So having seen the classifications of organic compounds, we shall now dive into discussing what we mean by the term homologous series. What do we mean by the word homologous series? Talking about a homolog, we can say that a homolog or homologous series is simply a family of organic compounds in which each member in that family differs from the next member by a CH2. That is the simple definition of a homologous series. In a given family of organic compound, each member of that family differs from the next immediate member by just a CH2. That is to say, if I have in a given organic family, I have the first member there, member A, and I add CH2 to its formula, to the formula of member A, the next member is going to give me, who is likely member B. We have a formula which is BCH2. And if I'm going to know the next member of that family, adding CH2 to BCH2, the next member of the family, which is likely C, is going to give me C2H4. That is just what it's going to give me. So what we are trying to say is, in any given homologous family, each member differs from the next member by a CH2. So we are going to take a look at examples of homologous series so that we can get to understand what this homologous series is all about. Examples of homologous series are alkanes, alkenes, alkynes, alkanols, also called alcohols, alkanals, also called aldehydes, alkanones, also called ketones, alkanoic acids, also called carboxylic acids, amines, amides, alkyl halides, esters, ethers, etc. So these are examples of homologous series. Once again, we said homologous series is a family of organic compounds in which each member in any of the family differs from the next person in that family by a CH2. Since they all differ by a CH2, it means they follow a structural regular pattern. Since they all differ from themselves by a CH2, it implies that they follow a regular structural pattern. So we can, for real now, say homologous series is a family of organic compounds which follows a regular structural pattern in which each successive member differs in its molecular formula from the next member by a CH2 group. That is it. That is what we refer to as homologous series. And we have just seen examples of homologous series. So having seen the examples of homologous series, we are going to be looking at each member, each family of this homologous series, and we will also consider the members in each family. But before we go to looking at that, let us take a brief look at the features of organic compounds. What are the features of organic compounds? We can also say characteristics of organic compounds. So what are these features of organic compounds? Generally speaking, organic compounds have low melting and boiling points compared to inorganic compounds. So if we are to compare organic and inorganic compounds in reactions, organic compounds seem to have low melting and boiling point. That does not mean their boiling and melting points may not be high, but in comparison with their inorganic counterparts, they seem to have lower melting and boiling points generally. In terms of flammability, organic compounds are flammable, very flammable. And of course, we can draw examples from diesel, kerosene, petrol, even crude oil. All these compounds are flammable. Our clothes, our books, our shoes, they are all flammable. The wood, the furniture, they are all flammable. So all these things can burn. Since they can burn, we say organic compounds are very flammable. They are not like metals that are not really flammable, that cannot really burn. Organic compounds are also thermally unstable. That is to say, they are characterized with thermal instability. What do we mean by thermal instability? By thermal instability, we refer to the inability of the compound to stay under intense heat without being breaking down. But most organic compounds, when they are subjected to heat, they break down, they decompose to give smaller organic compounds. That is what we refer to as thermal instability. A good example of this feature is as we can see in crude oil. Crude oil is a hydrocarbon petroleum. When it is subjected to fractional distillation, of course, from it we can get other hydrocarbons from there. We can get our petrol, diesel, kerosene, naphtha, petroleum gases, etc. So that is what is referred to as thermal instability. In terms of reactivity, organic compounds are reactive but not as reactive as their counterpart inorganic compounds. That is in terms of reactivity. And then when we talk about polarity, organic compounds are said to be non-polar. The question now is, what do we mean by polarity? Polarity is the ability of a compound or any given species to have partial positive and partial negative charge. Water, for example, is said to be polar because when it splits through electrolysis, it can go down to hydrogen ion and hydroxyl ion. Acids and bases also and salts, when they ionize in water, they also go into their ionic state, positive and negative charge. So organic compounds on their own do not possess this property, so they are said to be non-polar. However, there are few exceptions, and some compounds actually are organic compounds, but they possess this polar nature. For that reason, they can dissolve in compounds like water instead of dissolving in their fellow organic compounds. Generally, a polar compound will dissolve a polar compound, and as it is said in chemistry, like dissolves like. A polar compound will dissolve a polar compound, and a non-polar compound will dissolve a non-polar compound. But organic compounds like sugar will dissolve in water, as even we can use sugar in our tea. It is possible because sugar is, though an organic compound, but it is polar in nature. Since it is polar in nature, it can dissolve in water. So generally, organic compounds are non-polar, though there are few exceptions, and those exceptions is like sugar is an organic compound, but it is polar, hence it can dissolve in water. Alcohol, for example, ethanol, is an organic compound, though, but it is polar in nature, and for that reason, it can dissolve in water. So these compounds are said to be polar in nature because they possess an electronegative species in their structure. Water and ethanol, for example, possess an electronegative species, which is a hydroxyl group in their structure. So for that reason, they readily will dissolve in water. But other hydrocarbons or organic compounds that do not possess this species in their compounds will not dissolve in water because they do not possess the polarity of dissolving in water. Lastly, the covalent nature of organic compounds. Organic compounds are said to be covalent in nature because they tend to form covalent bonding. The carbon atom binds with itself covalently, and even when carbon and hydrogen binds, they come together in combination in the covalent kind of combination. So generally, these hydrocarbons or organic compounds form stable covalent bonding with each other. They do not form electrovalent bonding or any kind of bonding like metallic bonding or whatsoever, but they are characterized with the possession of strong covalent bonding. So these are the features, or we can say characteristics, of organic compounds. Having seen that, we shall now take a look at the characteristics of homologous series, which we've discussed before. Talking about homologous series, we have said it is a family of organic compounds which follow a regular structural pattern in which each member in any of these families differ from the next member in that same family by a CH2 group. So, having seen that, let us take a look at the common characteristics of homologous families or homologous series. The first we shall be looking at is their physical property. In each family of any homologous series, the members differ from themselves in their physical property just slightly. This is as a result of the increase in their carbon atom. The first member in a given family, for example, may have 2 carbon atoms. The next will have 3 carbon atoms. The next 4, 5, 6, 7, etc. So, the member having 2 carbon atoms will have slight difference from the member having 3 carbon atoms. This is because the difference in their carbon atom, which is just maybe 1 carbon atom or 2 carbon atoms, will go a long way to create that little difference. So the addition of 1 carbon atom to a compound will make it have a slight difference from the preceding compound. In terms of solubility, for example, let's take a look at the first homologous family, alkanes. Alkanes are saturated compounds. We shall get to talk about them very soon. They are saturated compounds. And in the family of alkanes, the first member is CH4, followed by C2H6, next C3H8, and then C4H10, and C5H12. These are first 5 members in alkane family. The first member, CH4, is called methane. The second is ethane, and then propane, butane, and lastly pentane, who is the 5th member in that family. with the molecular formula C5H12. In terms of their solubility, methane is readily soluble in comparison to the others. So solubility decreases as you go from methane to pentane. Reason being that as carbon atom increases, for example, between methane and ethane, CH4 and C2H6, as carbon atom increases, ethane, who is C2H6, finds it difficult to dissolve in water. But in as far as methane even is not readily soluble in water, it may interact with water better than ethane. And ethane will interact with water better than propane, C3H8. Similarly, propane will interact with water better than butane, C4H10. And it continues that way. The reason is as a result of increase in their carbon atom. So as carbon atom increases, their solubility in water decreases. Similarly, melting and boiling point also will be increasing from methane. Methane, since it is having only one carbon atom with 4 hydrogens, we tend to have a lower melting and boiling point compared to ethane, who is having 2 carbon atoms and 6 hydrogen atoms. So it tells us that for ethane to melt, there must be higher temperature to melt it compared to methane, who is just 1 carbon atom and 4 hydrogen atoms. So the temperature needed to melt methane, who is 1 carbon atom and 4 hydrogen atoms, will be less compared to the one that will be needed for ethane with 2 carbon atoms and 6 hydrogen atoms. So these are examples of the differences that each family, each member in a given family will have in terms of a homologous family. So having seen physical properties, let us consider their chemical properties. Chemical properties of the members of any homologous family are similar. They are similar because they tend to have the same method of preparation. They also have the same molecular formula. So their chemical properties are similar. Why? Their chemical properties seem to be similar because they generally have a kind of general method of preparation, and they also have a general molecular formula. That is a third property or characteristics of homologosity. In each family, all members share the same general method of preparation. Their general molecular, like we said before, is the same. They have the same general molecular formula. And lastly, each member in any homologous series differ from themselves by just the addition, or if you wish to say subtraction of CH2. If I add CH2 to a first member, I get the second member. If I remove CH2 from the second member, I get the previous member of that family. So they differ from themselves by a CH2 group. So these are the general characteristics of a homologous series.